Hi everyone, I'm Gangidi. I'm a production network engineer at Meta. I help build and scale AI training infrastructure with a focus on RDMA networking. I'm here to speak about our experiences scaling RoCE V2 in large scale production. 4 years back, we changed the way we did AI training at Meta, especially in our production environment. We moved from an AI training approach that was more suited for horizontal scaling to an approach that required vertical scaling. Meta has used RDMA with InfiniBand for many years and continues to do so for our research clusters. But this pivot to new AI training approach meant that we had to scale our RDMA infrastructure in production environment. So we deployed a dedicated network capable of supporting RDMA over converged Ethernet. Building on top of commodity Ethernet meant that we could leverage years of experience operating Ethernet infra and enjoy the multi-vendor diversity here as well. Initial deployments were consumed quickly, and more AI training use cases pivoted to using RoCE-based infra, creating immense demand. We have built RDMA fabrics that scale up to tens of thousands of GPUs, and we have many such fabrics. This large scale has brought with it plethora of new challenges and learnings. 3 generations of RoCE deployments down, I'm here to show you the highlights of our journey from design constraints to scaling challenges. This talk has 2 parts. In the first part, we introduce AI training and the constraints it puts on the network and how that has shaped our design. In the second part, we talk about some of our top operational challenges and solutions. So, where do we use AI training and inference at Meta? Everywhere. At Meta, we use AI training and inference to help create positive social experiences to our users. We do this across our family of apps. Some of the most important use cases include ranking for recommendation and content understanding. These experiences that AI powers are constantly evolving. Breakthroughs in generative AI and large language models are unlocking a new set of capabilities. AI training is a process of learning a new capability to predict some insight or recognize a pattern. And this is done from existing data. AI inference, on the other hand, is a process of applying the learned capability to make predictions on new data, real time. The size of the data sets that AI training operates on are much larger compared to that of the inference. For the purposes of this talk, let's focus on AI training and learn a little bit about what it entails. AI training is typically a background activity and can take many hours to days to complete. It is a mathematically complex process and it involves a lot of recursion and repetition. For this reason, AI training scales vertically with HPC style parallel processing semantics. Let us talk about how AI training is implemented. An untrained model with configurable weights is ported to a GPU worker. This worker needs to be fed large amounts of data. Realistically, you cannot feed all this data to the worker all at once. So you need to do this in chunks, and we refer to these chunks as batches. Worker performs recurring computational operations to tweak the weights of the model using each batch of data. This process continues until the model is perfected and starts making better predictions, and until it does so consistently. As the amount of data to be trained increases, doing this on a single GPU can become a very slow process. The model engineers training the model have to wait much longer to understand how effective their training strategy is. As the number of the parameters and of the weights in the model increases, it may not be even practical to fit this training process into a single GPU. For example, the Llama 2 model that Meta recently open sourced has 70 billion parameters. To solve this, we need distribute the training process over multiple GPUs. We can parallelize and distribute the model or the data, or a combination of both over multiple GPUs. This helps us speed the training process. Whatever the distributed training strategy is, all the GPUs are still working towards a common goal to produce a single optimized training model. So they cannot make optimizations independently. Within each training iteration, as they process data, they need to keep their state synchronized with all other GPUs, and they need to do this multiple times. This means transferring large amounts of data within a few milliseconds and doing this again and again between all the GPUs. This demands a network that produces high bandwidth, low and predictable latency. Failing to do so can leave the expensive GPU compute resources stranded. So how do we achieve these constraints needed for GPU-GPU communication? We achieve low latency using RDMA via kernel and CPU bypass. We can bypass CPU from the data path by using GPU to NIC peer-to-peer DMA. This helps us achieve high bandwidth. And as a side effect of all this, we can also use the free CPU cycles to feed the data to the GPUs on our regular TCP/IP network. Predictable latency can be achieved by avoiding congestion drops by using priority flow control or PFC. RoCE v2, the choice of our RDMA transport, has go back N loss recovery mechanism, which can be expensive. So it is very, very important to tune the PFC just right in order to avoid congestion drops altogether. There are two broad categories of models of Meta, and they produce different traffic patterns. We have ranking models that scale to hundreds of GPUs and are dominated by full mesh network patterns. They have hierarchical patterns too, but those can be pipelined with other compute activities in the application. And then we have content understanding and generative AI models. These can scale up to thousands of GPUs and primarily produce hierarchical or recursive patterns. There are three things I would like to highlight about some of the example traffic patterns found in our network. First, different traffic patterns produce different amount of flow entropy. Full mesh traffic patterns have more simultaneous flows and are hence easier to route via hashing schemes. Hierarchical traffic patterns, however, produce elephant flows and hence they're harder to route for a hashing scheme. Second part, different traffic patterns produce different amount of congestion. For example, the full mesh patterns produce partial incast. Hierarchical tree on the other side, can produce 2-to-1 incast. For this reason, we need DCQCN for congestion control to provide optimal tail latency even in case of the congestion. And the third observation that I would like to highlight is that the rings, trees, or any recursive patterns that are not highlighted here don't need a fully balanced network to scale. They need high injection bandwidth, but can tolerate increasing oversubscription in the higher layers of spine. In this slide, you can see how all the constraints AI training brings forth have shaped our network design. We have built 3 generations of endpoints with high speeds to offer high bandwidth. Each of our endpoint servers have 8 GPUs and 8 NICs. GPUs communicate within the same server via a shared memory fabric and across the servers via RDMA. Our topology is balanced first 2 network hops to support full mesh collectives that are part of the ranking workloads. We have 1 link mapping each TOR to a spine switch, totaling 16 links per TOR. Beyond the 2 hops, we use oversubscription because at that scale, hierarchical collectives dominate, and those can tolerate oversubscription as we just learned. For routing, we started with static routing, but we are pivoting away 2 approaches in different scenarios. These approaches are traffic engineering and ECMP based on QPair ID. We use RoCE v2 transport to offer low and predictable latency. We deal with congestion produced by the full mesh and the hierarchical collectives using DCQCN, which refers to reacting to a congestion with ECN marking before priority flow control can kick in for more extreme congestion scenarios. So now that we've learned about our deployment and what shaped it, so what are our challenges? Our challenges in scaling RDMA-based deployments are fairly highlighted by our load balancing and network routing issues. This has been the hardest problem for us due to the presence of elephant flows that are part of hierarchical collectives. Other challenges include slow receivers and the backpressure they produce. We have noticed that the slow receiver issues can happen due to application errors in memory allocation. That kind of points to how integrated this whole system is. This system is not just about RDMA, but it's about the GPUs. It's about the PCIe layer that connects the GPUs to the NICs and the backpressure that NICs produce and the impact that it has on the network. Coming to our third problem, although we have been able to avoid congestion drops, packet drops still happen due to physical layer issues. Go back and recovery mechanism means that that loss is very expensive. We have observed live logs in our network that caused performance regressions. These were mainly caused by drops in the in-switch links. Overall, the debuggability of the solution is challenging. This is because of synchronous traffic patterns that we learned about involving multiple senders and multiple receivers at the same time. It is hard to triage if a performance regression was caused by endpoint slowdown or slow network medium. This is particularly hard when slow senders are involved. We have developed various RDMA and verbs tracing capabilities to identify such slow senders that are causing regressions. Similar challenges apply for identifying a root cause for a job failure as well, not just job slowdown. So let's dive deep into a couple of our challenges, starting with load balancing. We started with a static routing scheme that would map the Tor downlink traffic to uplinks based on the destination IP prefix. We have one link mapping a Tor to a given spine switch, totaling 16 uplinks per Tor, as we just learned. Our network has 16 IP prefixes to account for 16 slices of the network. So once the Tor is able to make the load balancing decision for traffic injected by the NIC, and it does so based on the destination IP prefix, the rest of the path is deterministic. For the network traffic affected by failures, we just ECMP that traffic. And we ECMP the traffic only impacted by failures. Rest of the traffic continues to get statically routed. So how does this fare at scale? We noticed that this works well when the destination prefixes are evenly distributed. But in corner cases, the destination servers are not evenly distributed across IP prefixes. For example, as shown in this slide, we have server 1, 2, 3, and 5 sharing a job. While 1 and 2 are evenly distributed, 3 and 5 are distributed across partial set of destination prefixes, the first 8. This can result in 2-to-1 oversubscription of Tor uplinks as it's seeing congestion. This gets worse when one of the oversubscribed links fails and spills over into other oversubscribed links, if those flows are elephant flows. In corner cases with failures, you could see worst case of 3-to-1 oversubscription of Tor uplinks. We attempted to make scheduler modifications to achieve a more uniform distribution of servers with the destination IP prefixes on a job-to-job basis. But that wasn't scalable. As we deployed more and more servers, what we noticed is that one of the servers would go into repair. When one server goes into repair, its neighbor could not be left unused. So this wasn't a scalable solution. To solve this more longer term, we have two approaches. A software-based controller that programs routes based on scheduling signals. We began with first hop traffic engineering due to the nature of our two-stage flow. But we will look towards extending as our future network designs evolve. A traffic engineering solution will scale for AI training because it is a repetitive process, producing similar group traffic patterns, iteration over iteration. So you don't need to update the route program every few minutes. You can program it once, and it will last for a duration of the job, or when a network event happens, like a failure, whichever comes first. The second approach to scaling ECMP is by realizing more flow entropy with existing workloads, and by doing so with flow multiplexing. This solution involves two parts: Q-pair multiplexing for hierarchical traffic patterns, and generating better flow hashing by hashing on the Q-pair ID that is part of the RoCE v2 IB payload. So how do we implement flow multiplexing to help ECMP? We have two flow multiplexing or QP scaling techniques. One of them involves applications splitting each message meant to be posted over a single queue into multiple queues, resulting in multiple flows. This shows very weak scalability beyond a factor of 4, as it decreases the message size and increases the number of message size by the same factor. It also needs more acknowledgements. For training jobs, posting small messages, this is not optimal at all and will cause performance regressions. The second approach involves posting each message to a different queue and doing so round robin. This approach shows better scalability. We have been able to achieve a flow multiplexing factor of 64 with this approach. We were able to train the recently open source Llama generative AI models with this approach. While these techniques for load balancing are how we are solving for our current day topologies, we have been looking at different load balancing approaches for our future deployments. This includes an approach to spray the contents of the packet at the first network switch hop and to reassemble at the last network switch hop. This approach requires end-to-end admission control, and disaggregated schedule fabrics are a great way of achieving it. Another approach that we are investing in longer term is custom transports that can tolerate out of order delivery. So the second problem that I wanted to discuss is slow receivers and the back pressure that they create. In our deployment, we had noticed a case where some of our NICs were pausing the network 20% of the total duration. And this was happening constantly and consistently. The NIC speed was 400 gig, and the PCIe speed supporting the NIC and connecting it to the GPU was PCIe Gen 5. So there was no reason for why we should see TX pause. There was no reason why the NIC should be bottlenecked and indicating the network that it needs to slow down. When we dig deeper into this, what we understood was that there was no hardware malfunctioning here. The transport was working fine. What we noticed was that the application was greedily allocating GPU memory, almost close to the limit. And that resulted in GPU memory pressure. The GPU memory pressure in turn resulted in PCI pressure because the NIC needs to DMA traffic to GPU memory. And when it's not able to do so, there's PCI pressure. The PCI pressure in turn translated as network pressure. And that resulted in TX pause. So what is the impact of this persistent TX pause? In our networks, the impact of constant TX pause is limited. And the reason is that we have deep and statically carved spine buffer that absorbs back pressure. We also use ECN marking, but nevertheless, we have learned that having a statically carved non-blocking architecture in the spine really helps mitigate the impact of head-of-line blocking. So we learned about some of the challenges in scaling our RDMA infrastructure with RoCE v2. But what are some of the well-known challenges with RoCE v2 that didn't have that significant an impact on our deployments? The first problem is head-of-line blocking. We just learned how statically carved buffers and PFC watchdog that we also have in place helps deal with head-of-line blocking. Head-of-line blocking is a very rare phenomenon in our network. Tuning congestion control was something that we were also expecting to be a very hard process. PFC seems to do the trick. DCQCN is enabled in background for extreme congestion scenarios. We tried to tune DCQCN more tighter so that PFCs can never kick in. But nevertheless, that resulted in some of our workloads, especially the hierarchical collectives or hierarchical network primitives, running slower, even in steady state. So we relaxed the DCQCN thresholds and the network has been fairly in steady state at that point. Another problem about RoCE v2 that's mentioned in academia quite widely is about scaling to a large node count in a job. And the reason that's quoted that this will be a problem is a NIC Q-pair cache limitation. There's a couple of reasons why this has not been a big problem for us. The modern NICs have increased the size of their QP cache. So it really helps to be able to scale to many simultaneous connections. Our traffic patterns also are scaling in a way where hierarchical patterns are dominating at larger scale. producing limited amount of connections or limited number of queue pairs in the NIC. That also helps us scale to a very large node count. So to recap, we've designed and scaled RoCE V2 for our workloads with very unique constraints. We ran into lots of operational challenges, with load balancing being the main one, and we have solutions for each of them. We also have more longer-term solutions to these problems in the horizon. In summary, we want Meta to be an example that commodity Ethernet deployments can scale for supporting large-scale training. Multiple challenges remain, but solutions are on horizon. If you'd like to share more of your learnings with RDMA deployments, or if you want to learn more about our observations, please get in touch. Thank you for listening and enjoy the rest of the conference.